Hey there, physics students. Let's go ahead and review the next FRQ practice question in preparation for the AP Physics 1 exam. Let's see what we have. It says, the left end of a uniform rod of length d and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot as shown. Point C marks the center or midpoint of the rod. The rod is initially motionless, but it is free to rotate around the pivot. A student will slide a disk of mass m disk toward the rod with a velocity v0 perpendicular to the rod, and the disk will stick to the rod a distance x from the pivot. The student's goal is for the rod disk system to achieve as great an angular speed as possible. Okay, so a couple of things. Before we even read the questions, let's just identify what's going on here. So first of all, we know the disk is coming in at the rod. The rod is not going to slide. The rod is going to rotate, okay? And it's going to rotate around this frictionless pivot. Now, the first thing they tell us is that the disk is going to stick to the rod. And when the disk sticks to the rod, you know that we have a certain type of collision. And so that should trigger your brain into thinking about momentum, because of course we're going to have a conservation of momentum. Now, we've got some linear momentum here, but there's also angular momentum that's gonna change when we hit the rod with the disk. The other thing you might think about is if this thing is going to rotate and it's initially motionless, then the disk is going to have to impart a torque onto the rod. And we know that torque is going to be due to the force that the disk exerts on the rod times the distance, the lever arm, the radius of action from the pivot point. Okay, so there are two ways to look at this. Okay, so let's just talk about those two things first. Okay, so first of all, let's talk about the torque, because I think that's the first subject that we talked about with respect to this type of motion. And we know that torque is equal to force times lever arm. Okay, and in this case, the force is going to be imparted by the impact of the disk. It could be force times delta t, or an impulse that's impacted. And then the length that it impacts is going to be this distance x away from the pivot. So if we want to have the most angular speed, that achieve as great an angular speed as possible, if we want the angular speed to go up, that means we want omega to be as big as possible. We want to make sure that we maximize the torque, because the torque is going to change that angular speed, or change the angular motion. Now, we can throw the disk as fast as we possibly can. So that's going to help with the force, because that's going to give it more momentum. We know it's going to stick, so we've got one of those inelastic type of collisions. And we know that the other component of torque is the lever arm, this distance x. So we know that we could actually rewrite this as the force times x in this case. Okay, so that's our concept of torque. Now, the other concept that we have is, of course, momentum. And we know that P equals mv. And so the disk has some particular momentum that it has when it's going in here. But one thing we want to make sure we understand is that when this disk hits this rod, this is going to cause a change in angular momentum. So we need to talk about the L, which is I, the rotational inertia, times omega, whatever the speed is. Okay, and we know that we can calculate the momentum of this thing moving, because of course we're going to have the inertia. We're given the rotational inertia of the rod. We know that it's going to be rotating, so we know we could find some angular momentum. What you may have forgotten about the torque and rotational dynamics unit is that this disk, this object moving in a straight line, sure, it has linear momentum, but it also has angular momentum about the pivot, meaning when it hits that rod, it's going to have an initial angular momentum based on its rotational inertia around the pivot, because it's going to stick, and the speed that it's going according to what's happening here. Now, when the disk is just about to hit the rod, it's not moving in a circle, it's not moving angularly, but we can interpret what that angular momentum is by just solving for the angular momentum of the disk using what we know. So let's just talk about the angular momentum of the disk. So let's just pretend this is the disk. And we know that the moment of inertia of a point object is really just m times r squared. Let me just write this as moment of inertia. M times r squared. So that's the when this disk hits the rod and it's going to start spinning, the moment of inertia, the part of that disk, is going to be mr squared. That's the rotational inertia because it's a point mass. And what's the mass? Well, the m is just the mass of the disk. The r is just the distance. So again, we could rewrite this as m of the disk times x squared. Okay, so that's cool. But what about the omega? Well, we know when the disk hits and sticks and it starts to rotate, it is going to have a speed omega. So what is the omega of the disk? Okay, so if that's the moment of inertia of the disk, what's the omega of the disk? Well, we know that it is the angular speed, but let's not forget our rotational analogs, and remember that in fact the angular speed is just the linear speed or the tangential speed of a rotating object divided by the radius around which it rotates. And let's not forget that the radius in this case when it hits the disk, or the rod, pardon me, is just going to be x, so we can redefine this as v over x. Now, if we look, the angular momentum of the disk is I times omega when it hits the disk, when it hits the rod. So we can really substitute these things in. So if we say I times is mr squared or mx squared, so we know that that's mx squared, and that's our I value. And then we can plug in for omega, we can plug in v over x, and we see that lo and behold, the squared goes away and one of the x's goes away. So we end up with the momentum of the disk, the initial momentum of the disk when it hits that. Sure, it's going to be m times v, but it's also going to be, for angular speed, because that's what kind of collision we have, a change in angular momentum, it's going to be mx times v. Okay, so these two concepts, the momentum of the disk and the torque equaling the force times the distance, are going to be good concepts to remember when we start answering these questions. So I'm just going to leave this scratch paper here while we take a look at the rest of this. And the first question they say is, suppose that the rod is much more massive than the disk. It says to give the rod as much angular speed as possible, remember that's the goal, the student should the student make the disk hit the rod to the left of point C, so over here, at point C, or to the right of point C? Well, let's think about what we want. We want the biggest omega possible. Well, the biggest omega possible is going to come from the biggest torque possible. Okay, and if we look at our description of torque, we know that the distance that it hits from the pivot is x. So if we want the biggest torque, we want the biggest x. So that's going to tend to mean the right of C. So in terms of torque, it would be to the right of C. Okay, I'm going to go ahead and check that because that makes sense with torque. However, let's take a look at momentum. If we know that we want the biggest change in momentum of the rod, we want to make sure that the disk has the biggest momentum going in. And we know we could change the speed, but that's not what they're talking about to change the momentum if we're talking about linear momentum. We can't change the mass of the disk, so we got to think about angular momentum. And if we think about it in terms of angular momentum, take a look. Angular momentum of the disk, L, is mxv. Again, x is going to, if x gets bigger, then the momentum gets bigger. So again, that leads us to answer choice to the right of C, because both of those are going to give us a greater resulting angular speed. Okay, it says briefly explain your reasoning without manipulating equations. Oh darn, look at all the work I did with equations. Well, we'll hold on to that and we'll think about that in a bit. But let's think about what we want to do. So let's talk about it in terms of torque. Let's just do both methods, okay? So we could say that the reasoning without manipulating equations. So we could say, now I'm gonna outline this. Again, I don't want to spend time writing out sentences because that takes up too much video time, but and because you can end up pausing it and coming back. But here we go. So if we talk about it in terms of torque, we know that a bigger angular speed, a bigger change in angular speed is going to require a bigger torque. Okay? And in order to get a bigger torque, the only thing we can change, because they're asking us for this distance, this x, the torque is going to get bigger if the x gets bigger. So we want the x to get bigger if the torque gets bigger. So we could say something like the torque is going to have to increase to get the bigger change in momentum or change in angular velocity. And in order to get a bigger torque, the only factor we can change is the distance from the pivot, and that's the x. So we want the biggest pivot possible. So that means right of C. Okay, so that's the torque way of looking at it. And again, you would want to write this out in a couple of sentences and trying to just use words to describe this and not use equations. Again, I'm going fast because I want to make sure that we get through this in a timely manner. Okay, the other way we could do it is from momentum. Okay, and we know that if there's momentum, we know that momentum is conserved. Okay, so L naught equals LF, however you want to describe it. So the momentum is conserved. So the total momentum of the system before it hits is just the momentum of the disk. That's the LD or the MXV. The final momentum is whatever the total inertia is times the speed. Okay, so we know that the total momentum in the beginning is mxv, because that's the momentum of the disk, and the final momentum is going to be the total rotational inertia, because remember, it's going to stick. Okay, so it's going to be the total rotational inertia times the omega. Well, let's take a look at what our factors are here. Again, you're not supposed to use equations, but you're just going to want to say. So look, if we know that x gets bigger, then the change in angular velocity, change in momentum is going to be bigger. Okay, so the change in momentum is going to be bigger. So that first, the initial momentum is all in the disk. The disk is going to lose all of its momentum to the rod. So we basically can say that if x is bigger, and again, you're going to use words to describe this, then the L disk is bigger, and therefore the delta L of the rod is going to be bigger, and that means the omega is bigger. Okay. Now I know they told us not to use equations, but again, those are just symbols and an outline for how you might want to describe that in words. Okay, you might say something like the total momentum is conserved, the momentum is entirely contained in the disk. When the disk hits the rod, it loses its momentum and gives it to the rod. The greater the momentum of the rod, the greater the angular speed. And in order to do that, to maximize the momentum of the disk, we're going to maximize the distance. Okay? So that's the general idea. Okay. It says on the internet, that's always suspect, a student finds the following equation for the post-collision angular speed omega of the rod in this situation. It says omega equals m disk times x times v naught. Hey, that's the momentum, if you remember, over the rotational inertia. Okay, well, that sounds pretty good, because if you look at this equation for momentum that I just wrote down, if you solve that for angular speed, that works. It says regardless of whether or not this equation for angular speed is correct, so we really don't care if it's correct or not, does it agree with your qualitative reasoning in part A above? In other words, does this equation for omega have the expected dependence as reasoned in part A above? Well, what did we talk about with part A? Part A, we talked about x, okay? So that's what we're really talking about for this. So let's take a look at this equation. This says if x gets bigger, then omega gets bigger. And that makes sense, because of course we said if it's to the right of C, we're going to get the biggest angular speed as possible. So yes, that equation works. Now you could talk about the velocity or the mass or the rotational. You could talk about all of those and you could compare those and all that, but that's not what the question asked for. The question asks about part A, and part A we were talking about x. Okay, and so we could say basically that the equation makes sense. Okay, because it says that when x gets bigger, then omega gets bigger, and that's in fact what happens. Again, you're going to want to be a little more eloquent than this, but again, a sentence or two so that you can hit the key points, that the x distance, which you talked about in part A, gets bigger, then omega gets bigger, and that's what the equation says, and that's what happens in the picture or in the event. Okay, next. Okay, here we go. This is a good reasoning question here. It says another student deriving an equation for the post-collision angular speed omega of the rod, makes a mistake. So the student makes a mistake and comes up with omega equals I x v naught, okay, times over m disk d to the fourth. It says, without deriving the correct equation, how can you tell that this equation is not plausible? In other words, why does this equation not make physical sense? Briefly explain your reasoning. Well, let's look again at these variables. Okay, well, what does this say? Well, this says, first of all, that if x gets bigger, if we're looking back at x again, if x gets bigger, omega gets bigger. Well, that's right. Okay, it also says if v gets bigger, omega gets bigger. Well, if v gets bigger, we know that the angular momentum of the disk, or even the linear momentum of the disk, is going to be bigger. So we're going to, that's okay. If you look at the mass of the disk, however, look at the mass of the disk flying in. This says if the mass of the disk is bigger, that would mean the omega, the angular speed of the rod after the collision, would be smaller. So that would be like saying a giant disk, maybe a bowling ball hitting a meter stick, would cause a smaller change in speed than a tiny, maybe a ping pong ball hitting, let's say, a baseball bat. Okay, well, that just doesn't make sense. Okay, so it does not make sense. Equation does not make sense. It's not plausible. Plausible, if you want to write this out. How do you spell plausible? P-L-A-U-S-I-B-L-E. Okay, not plausible because the equation says if m of the disk gets bigger, then omega gets smaller. Well, that just doesn't make sense because, of course, if what's true is that when m of the disk gets bigger, the angular momentum, also the linear momentum for that matter, gets bigger. And we already know that if the angular momentum or the linear momentum get bigger, we know that the angular speed is going to change more. Okay? Again, you're going to want to explain this in words. You can use some symbols, but you want to use words to talk about what's going on. Okay? All right, let's take a look at the back side. And okay, we got the same picture. And now this one says, for this part, do not assume that the rod is much more massive than the disk. In other words, they're closer in mass than being really different. Okay? So it says immediately before the collision with the rods, the disk's rotational inertia about the pivot is m disk times x squared. Hey, that's what we said. Okay, we said that the rotational inertia is mx squared. Okay, that's cool. And its angular momentum with respect to the pivot is m disk v naught times x. Well, that's the same thing here. I've just got them in different order. It doesn't really matter. It says derive an equation for the post-collision angular speed, omega, of the rod. Express your answer in terms of d, m disk, I, x, v naught, and physical constants as appropriate. Okay, so the only things that can be in our final answer are these and any physical constants, like the acceleration due to gravity or something like that. Okay, should those show up. Okay, now I know I just mentioned that we have some similar expressions. In other words, we had similar expression for moment of inertia of the disk. We had similar expression for the momentum of the disk. And remember I remarked that these were in a little bit different order. It's really important, if they tell you the equations to start with or they tell you the expressions to start with, you should start with those expressions, okay? So I'm going to go ahead and write those down first. Or use those in terms of what we have. Well, we know that when this process occurs, when the disk hits the rod, we know we've got a change in momentum. This is a collision, that's a conservation of momentum. Okay, so we can start out by saying L initial equals L final. Okay, the rotational momentum or the angular momentum initial equals the angular momentum final. Now, what do we got at the beginning? Well, we got two objects, right? We got the disk and we got the rod. And so what does the disk have? We know the disk has momentum m disk, and I'm just going to write d, v naught times x. The rod has what momentum when we begin, before the equal sign here? Well, the rod is not moving, so it has a 0 momentum. Now, after these two collide, we're going to end up with some final momentum. Let's not forget the equation for momentum is I omega. Okay? Now, in this kind of a collision, let's remember these stick, and when these stick, we're going to have an inelastic collision. That means this rotational inertia and the rod's rotational inertia are going to be combined. Okay? So what we have to do is, I would start out by just saying this all equals I times omega, but this is I total. Okay? Now what's I total after it hits? Well, we know the rod, they tell us the rod has moment of inertia I. So what's the total rotational inertia after it happens? Well, we know it's I, and then plus the rotational inertia of the disk, which we know they tell us is mdx squared. Okay? So now we're going to plug that in for I total. So now we can say md v naught x, no plus 0 is just what it is, times the total rotational inertia, which is I of the rod, plus mdx squared. And all of that, that's the total, all of that is times omega. And they want an equation for the angular speed. So the only thing we got to do is solve for omega, and when we do a little algebra, our omega is going to be equal to md v naught x over I plus mdx squared. And that's our equation. Okay? Shouldn't be too difficult as long as we start with what they tell us. And let's just check our variables. Yep, we only have I, x, and v, and md. Now we didn't use a d, but that doesn't come into play because we're not really concerned with the length of the rod because they give us the moment of inertia of the rod. Okay, that should be a plus just to make sure you guys can see that. Okay. All right. Oh, this is a good question. Okay, so this question asks us, it says, consider the collision for your equation in part D was derived. The collision for which your equation in part D was derived. Except now suppose that the disk bounces, okay, so it's not going to stick off the rod instead of sticking to the rod. It says, is the post-collision angular speed of the rod when the disk bounces off it, omega bounce, so the speed, if it bounces, greater than, equal to, or less than the post-collision of the angular speed of the rod when the disk sticks to it? So one of the things you might want to remember is we did a couple of these types of problems in class. One of them was called rubber bullet, where one bullet goes into the block of wood and one bullet bounces off the block of wood. But the key thing you want to think about is what's going to cause this angular speed? Well, the angular speed that's going to be caused by this collision, okay, is going to be caused by a change in momentum. Now, if the disk sticks, it's going to give it a certain angular speed, okay, because it's going to lose most of its momentum. If the disk bounces, okay, when the disk bounces, it's going to bounce back in the other direction. That's going to be a bigger change in momentum of the disk. So in the first part, the disk goes in and it just goes blah, and it sticks, okay? That means it's going to lose all of its forward momentum and it's going to transfer it to the disk rod system. The disk bouncing means it's going to start out going in and then it's going to hit and then it's going to be coming back, and the disk will have a speed in the opposite direction. Well, that's a bigger change in momentum because it starts out going up in this case and ends up going down, or counterclockwise and then clockwise. Okay, so the bouncing is going to be a bigger change in momentum, so that should give us a bigger change in angular speed. So I'm going to say the omega bounce is greater than the omega stick. Okay, so the way you want to think about this, the only real way that you can think about this is momentum. Okay, so you know in any collision, momentum is conserved. Okay, so L initial equals L final. Again, you might want to say momentum is conserved for when the disk bounces. That is a bigger change of momentum, a greater change of momentum, so greater delta momentum, let's just put delta L, okay, than sticking. Okay, when it bounces, it has a greater change in momentum. The change in momentum, okay, if the change in momentum is greater, that means the omega is going to be greater. Okay. You could also talk about direction, because it bounces back and it causes a clockwise and counterclockwise torque, but that's going to be a little harder to describe. And essentially, you're going to have a hard time using torque because you're going to have to talk about the change in angular velocity, and that's a little hard to get at without angular acceleration. So the easiest way to do it is with momentum. Now, again, all of these written answers should be a little more eloquent than what I've written on these papers here. These, you can think of these as bullet points, outlines, outline points that you're going to want to explain with a few sentences or so. Make sure you use subjects and verbs. Use correct terminology. And then the only other thing to remember is whenever you're doing a derivation, start with the variables that they give you or the expressions that they give you, whether or not you created your own on some reasoning scratch paper or reasoning strategies before. Okay, thanks for listening. Thanks for watching. We'll see you next time.